Now, let's get into the main process of proving the Kakeya set conjecture. First, I'll classify what Kakeya sets are. Second, I will introduce the algebraic tools that may be really effective. Third, I'll break the problem down, and finally conclude the paths that lead to the result we want. Can also be called Basikovich sets are all the unit vectors that have different directions. You can arrange their position at any place you like, on certain functions or on the parent tree mentioned in the previous sections.
Alright, let's start with the big ideas. When mathematicians want to prove a conjecture, a classic move is proof by contradiction. For the Kakeya conjecture, this is pretty straightforward. We assume there is a three-dimensional Kakeya set whose Hausdorff or Minkowski dimension is less than 3. Then show that assumption leads to a contradiction. How do we prove it? Sometimes it's easier to translate geometry into algebra. Because let's face it, we can't just keep thinking about samurai swords and ancient Japanese warriors in a math problem forever, right? That's where the ideas of dimension help us. Minkowski's dimension basically tells us dimension is tied to scales. Imagine a single line in three-dimensional space. It's still one-dimensional, but add a bunch of more lines, each a bit tilted differently. Suddenly, the collection of one-dimensional lines can fill out a plane, which is two-dimensional, or even a chunk of three-dimensional space. Adding lines with different directions adds what we call complexity. More complexity means higher dimension, which is exactly what the conjecture is after. Complexity sounds cool, but it's kind of vague, right? Mathematicians like to replace it with something precise, which is discreteness. Back to our lines example, how different are those lines? At what scale do those differences matter for dimension? Here's a theory called the Borgen theory that puts numbers on discreteness. It says if a set is discretized enough, then either the set you get by adding any two elements from it, or the set you get by multiplying any two elements from it, is much bigger than the original set. Now, what do I mean by the sum set and the product set? Simple. The sum set contains all possible sums you can make by adding two elements from the set, and the product set contains all possible products you can get by multiplying two elements from the set. For example, if our set contains just three numbers 1, 2, and 3, then the sum set is 2, 3, 4, 5, and 6, all the sums you can get by adding two numbers from our set. The product set is 1, 2, 3, 4, 6, 9, all the products you can get by multiplying any two numbers from our set. You may notice that the product set has almost double the size of the original set. That's discreteness in action. The set expands when you add or multiply elements. Some sets aren't discrete at all, like groups, because in groups, adding elements together keep you inside the group. So the sum set doesn't get bigger. For instance, the group of all integers added to itself is still the group of all integers. That is everything about the Borgen theory, and it's not hard to understand. But to make Borgen's theory work on the Kakeya set, we need to fit in those conditions of the Borgen theory, that the Kakeya sets are discrete. During a process called discretizing, we can make that happen. How? As we all know that the number of unit vectors in the Kakeya set is infinitely many, and that's a real problem. It's really hard to analyze infinite many vectors. Mathematicians came up with a brilliant idea to solve this problem. Why not just gather some vectors together, say their angular difference is not larger than delta, and use another object to represent this set of vectors? Indeed, that's how delta tubes work. Delta tubes are basically prisms that have scale delta times 1, They contain all vectors that has a most angular difference delta, and this can be mathematically proven using the feature of sign function near 0. But to some convenience, I'm not going to prove it now. The number of delta tubes are limited, of course, because that's why we have delta tubes, and the number of delta tubes of a three-dimensional Kakeya set has the scale delta to the minus 2. And here's why. Because the surface area of the unit sphere is constant, and each delta tube covers an area about delta squared. So dividing the total surface area by area covered by one delta tube tells us how many tubes we have. Now that we have a finite number of delta tubes, what can we say about them? Like the unit vectors they represent, delta tubes differ from each other in directions by about delta. This difference is key to what comes next, known as the Wolf axiom. Can you imagine that how many places delta tubes will occupy if they do not intersect with each other? Well, mathematician Wolf gives the answer. In a prism that has length A, width B, and height delta, the total number of delta tubes of different directions that go through it while not intersecting significantly is AB over delta squared. Well, that's pretty easy to understand, right? Meaning that if the delta tubes are around vertical, the projection of the delta tubes onto the xy plane is around delta squared. And as you divide that to AB, you get AB over delta squared. But how is that related to the Kakeya conjecture? Clearly, the Wolf axiom is a restriction to a set of delta tubes that are at different directions. The Kakeya set, on the other hand, requires that every delta tubes that is representing vectors in the set have minimal angular difference delta. So if there are too many deltas in the prism we have just gave, then what will happen? Let's suppose we now have two delta tubes, TA and TB. TA has direction VA, which is the vector, and TB has a direction VB. We now put their bottom on the same surface and suppose the distance between the two bottom is vector A. Then, at the top of TA, it has a variance of vector VA because of the tilt, and the same for the TB. What we want is that TA does not intersect with TB, so we have the length of vector VA minus vector VB is smaller than the length of vector A. As we just said, there is an at least delta angular difference between the directions of delta tubes, and so is the minimal difference between VA and VB. The minimal difference of VA and VB is delta. Amazingly, we now have a length of vector A is larger than delta. We can imagine that there will be some point that there are two more delta tubes that they are less than delta separated, meaning their minimal angular difference is less than delta. And that contradicts with what delta tubes are. The Wolf axiom proves that a special compressed upper limit that makes the minimal dimension not too low. With the information in the Wolf axiom and the definition of Minkowski dimension, we will have a lower bound 2.5 for three-dimensional Kakeya set. And that's a big achievement. But 2.5 is not the result we want, right? Although it's quite a breakthrough. In 2000, Katz and Tao, two mathematicians, say that the Kakeya set conjecture might be solved using algebra, discrete math, and geometry. The Wolf axiom is that geometric approach, and if we want to get a higher lower bound, we will need to translate some of the geometric property into equations, or inequations. Remember in the second part we talked about Borgian theory, and that's the equation that inspired Katz and Tao. Now let's be specific. What Katz and Tao actually did was to classify the Kakeya sets. Of course, those delta tubes. They concluded three properties that affect the lower bound of the dimension of the Kakeya set: planiness, graininess, and stickiness. Planiness is about how many delta tubes a plane goes through. In this example, there are one certain plane that can go through all data tubes, and this Kakeya set is really plainy, in other words, dense on some certain plane. Graininess is similar, just change the plane to a very small object. Firstly, a grain is a small box that is roughly delta times 1 times 1, and it is just like the name, a grain. If you move the grain, and if you can find a spot that there are a lot of delta tubes intersect with the grain, then the Kakeya set is relatively grainy. The main aspect that had a great breakthrough these years is about stickiness. It's really easy to understand stickiness. As we have a finite set of delta tubes, can we cover all the space that delta tubes occupy with larger tubes called row tubes? It is hard to explain through words, but see the animation demonstrating stickiness. If we can assure the number of least row tubes to cover all delta tubes, then it's a way to describe how closely the delta tubes are close together. You may ask, how does the close together matter to the lower bound of dimension? That seems to be an upper bound restriction, isn't it? Indeed, it is against our intuition. And the main problem is on the scale delta. Delta is nearly zero in our imagination, and delta tubes are angular delta differentiated. But when a bunch of delta tubes aggregate, their volume is not that ignorable, but rather forms a bush. Just imagine 100 branches, and if you put all of them in large distance, you cannot say that they have a significant volume because each one of them have a small volume. But if you put them together, you can feel the volume of them, and that's the power of come together. Anyway, this is the relation that stickiness gives. It's really simple. If a set of delta tubes are sticky given a parameter theta, which is how sticky the delta tubes are, the lower bound of the Kakeya set is 3 minus delta, where theta is between 0 and 1. And now you see, the traditional stickiness cannot lead us to the final result of the three-dimensional Kakeya conjecture. So mathematicians came up with other approaches to kill the limit of stickiness, including those. We can see some familiar faces, the Born theory and the sum product theory. And there's algebra, geometry, discrete math, and so on, so many math branches. That's how a successful math problem contributes to math itself. It moves math studies in all aspects of math and combine to make the math problem itself complete.